All right, picking up where we left off on 4.1, talking about graphing systems of linear equations, let's look at the definition. A system of equations is, who can tell me the definition? Oh. Yeah, does anybody have what they say in the PowerPoint? A set of two or more related equations. Okay, like we have up here, they both have x and y, and we can graph them on the same axis. The definition, the solution of a system of equations is, yes, the point of intersection. Okay, and that's why we said here is the point of intersection, and then that means that that's the solution, is that ordered pair. And remember that we can plug that number into both equations to check. So I expect always to see people checking to see if they got the right answer. Okay, let's go on to page 2. Let's look at some special cases. And before we do this, let's just think about this for a moment. Two lines. How many times do two lines cross? Yeah, just once. Are there ever cases where two lines wouldn't cross? What kind of cases would that be? They're parallel. Do you remember what you know? What do you know about parallel lines? Same slope, because they have the same rate of change. So parallel lines are going to have no solution because they're not going to cross. Is there ever a time when an equation could have more than one solution? Okay, what would that be? A dependent system. But what does that even mean? Okay, think about it. Think about it. We'll answer that question just right now. Okay, so the first thing we're going to do is we're going to graph these two lines to find out what the solution is. We want to know where they cross. So my preference, again, you can graph these however you like. My preference is to always put them into slope y-intercept form. So I'm going to take this equation, the very first equation, I'm going to solve for y. Negative minus 6 x, I get negative 3y equals negative 6x plus 9. And then what am I going to do to get y by itself? Hopefully you said divide everything by negative 3. Ooh, isn't that nice when your fractions reduce to perfectly whole or negative numbers? Okay, not fractions. So we have, what is the coefficient here? 2x, good. And what's the y-intercept going to be? Or negative 3. Okay, so I go down here, I have negative 3 is my y-intercept. I'm going to rise 2, 1, 2. I'm going to run 1. Rise 2, 1, 2, run 1. Or I could also rise 4 over 2. Go up 4 over 2. All right, so I just need a few points to get my line graphed. And I'm going to do the exact same thing for the other equation. So this one right here, negative 2x plus y equals 8. I'm going to add 2x. I get y equals 2x plus 8. Oh, that wasn't too bad. So I go up here. Now there's no place for me to rise. I want to be able to rise from the y-intercept of 8. But do you guys know that the slope 2 over 1 is equivalent to negative 2 over negative 1. So I could go down 2, back 1, down 2, back 1, down 2, back 1. And if I plot those points correctly and I graph my line, I'm trying to find, what is the solution again? The solution is going to be where they cross. What do we know about these two lines? Why are they parallel? Yes, since they both have a slope of 2, same slope, slope means that they're parallel, and that means that they're never going to cross. Now you gave a fancy word for that system, which we're going to get to in just a moment, these different types of systems that we have, and the word you gave was inconsistent. An inconsistent system has no solution since the lines are parallel. So we can just say that this is, we want to name the system. It's an inconsistent system. Okay, let's look at example 2. Example 2, again, we want to go ahead and graph these equations. So x minus y equals 6. If I want to graph it using slope y-intercept, I'm going to subtract x from both sides. I get negative y equals negative x plus 6. Is y by itself right now? What do I need to do to get it by itself? I need to divide by negative 1, because I want the y to stay where it is. I don't want to add it because I don't want to get it to the other side, right? So I want y equals, what's the slope going to be? X, good. The slope is actually 1, right? Because it'd be 1 in front of the x. And then 6 divided by negative 1 is negative 6. So to graph this, we start here, negative 6. Now, if my slope is 1 and it's positive, remember it's going to go up from left to right. So if I rise 6 and run 6, isn't 6 over 6 the same thing as 1? So now I have 2 points, and I can graph my line. Okay, reviewing graphing. Is this helping to review graphing? Okay, questions so far? All right. Now let's look at this second equation. Negative 2x plus 2y equals negative 12. Any predictions before I start to get y by itself? What do you think is going to happen here? Okay, well, we don't want to divide by 2 just yet. Let's add 2x to both sides, right? Let's get y, isolate y. 2y equals 2x minus 12. What should I do to get y by itself now? Divide by 2. I want the y to stay where it's at, so I don't divide by y, right? Because otherwise I would get 1. Y equals 2 divided by 2 is 1x. And you could just leave it, when you have x is the same thing as 1x. What's negative 12 divided by 2? Oh my goodness, what just happened? These equations are the same. So what happens is, if you have the same line, how many times does that line intersect with itself? An infinite number of times. We call this what kind of system? Dependent. A dependent system has infinite solutions since the lines are the same. Okay? Now, what do you guys think about, we talked about inconsistent and we talked about dependent. Did I say dependent? Yes. Okay, so this one right here is dependent. This is example 2. I feel like I mixed up my words, but nobody heard me, so that's good. What about a consistent system? What do you guys think that one is? Yes, a system with one solution, and that solution is an ordered pair. Okay, it's the point where they intersect. So essentially, if you have the same line, it's going to intersect itself infinite number of times. If you have two different y-intercepts but the same slope, and that's why you really want to, I consider when you solve and get y by itself, when you put it into y equals mx plus b form, I think that's a check. Because that way you're able to see what is the slope, what is the y-intercept. It's really hard when the equations are written in standard form. We call this standard form. It's really hard to recognize what the slope is. You might see here that if I multiplied everything by -2, I get the exact same equation, but you might not notice that. So putting it into slope y-intercept form, for me, counts as a check. So graph them, put them in slope y-intercept form. That's going to be the best way to go. Okay, let's go ahead and look at the next problem. So we got some word problems here, everybody's favorite. Two friends purchase new cars on the same day. Glenn buys a Nimbus 2000 for $25,200, which depreciates at a rate of $1,800 per year. Bobby purchases a, how do you say that? Is that even a real car? A lemon. It's probably for lemon, right? It's a joke. For $32,400. Maybe it's a joke. I don't really know. The lemon depreciates by $3,600 per year. Construct a function to model the value. So this was a Math 60 thing. We talked about functions in Math 60. This is function notation. That's what they're asking for, a function. So function notation, it's essentially the same. N of x is the same thing as y, okay, using function notation. So we want to know after how many years what the value of the car is, of the Nimbus. So it starts out at 25,200. Every year it decreases by 1,800 per year. So what's the slope and what's the y-intercept there? Purchase price, good. Per year. Right. And it's going down, right? So that's why it's going to have a negative slope, isn't it? Now, the easiest way to graph, this is really hard to graph, and that point, that y-intercept, is probably totally inaccurate. Do you get why it would be inaccurate? Yeah, it's really hard. It is hard. I don't love the scale on this. What I would suggest we do is let's figure out how many years does it take for the car to be worth nothing. How would you calculate how long it would take for the car to be valueless? Yes. Yes. Divide 25. Yep. Divide by 1,800. Because that's going to tell us after 14 years. So you see that little trickiness that I did there? And it is really, really hard to graph. I would actually put that dot is almost, I mean, because it's not that much, 200 over. You know, and this scale, what scale are they using here? It's counting, every line is counting by 5,000. So that's why when I put that point up higher, that was very inaccurate. It's hard when you graph with a scale of 5,000, essentially. Okay? And by the way, I wouldn't really put arrows on the end of this because essentially, you know, hopefully the car is not going to be worth a negative value, and you can't really go back in time, right? Yes, do you have a question? Yes, down 1800 over 1, down 1800 over 1. The scale is not friendly for this. It's very, very tricky. In fact, I would probably, with a problem like this, I would prefer to go to graphing calculator, which I'm going to show you in a moment, okay? Now, what would be the function for the, and how would you guys say that? 32,000, so it's definitely not a lemon, right? Because it's a very expensive car. Minus 3,600 x. So again, our y-intercept is, well, and maybe that is actually kind of halfway, almost halfway in between, right? Do you see why that would go about halfway in between there? Okay. And then how could we figure out when it's, so that essentially when I'm figuring out when the value is 0, you see how right here the value is 0? I'm essentially finding the x-intercept. How long does it take for this car's value to be 0? Well, I would take 32,400 and I would divide it by 3,600. 9 years. So I'm halfway in between 8 and 9. Do you see how that's kind of like creative little workaround on how to find, if I find the x-intercept and the y-intercept, And I'm not putting arrows on these because, again, I don't want my value to be negative and I don't want my time to be negative. So that's why this is quadrant 1, right? Everything's positive, positive in quadrant 1. Graph both, did it. See, that's reading directions, including the scale, all right? Is the system of equation dependent, consistent, or inconsistent? It's consistent. Why do you say that it is consistent? Yes, 1 point of intersection. Okay, and here's that point of intersection, it looks like. Use the graph to determine when the two cars will have the same value. When? So after how many years will the cars have the same value? Yeah, after 4 years, the cars have the same value. I'm modeling for you writing incomplete sentences. What is the value, do you think, at that time? So here's the years. Here's the value. Right here we can say this is value, and this is years. We're labeling the axes, okay? What do you think the value is going to be? Yeah, it's hard. It is really hard to tell. Use the models to algebraically determine when the nimbus is worth 0. Actually, we already did that. It's 19,000. Because actually, if you plug in 4 to both, yeah? Oh. Right. Oh, 1,800. Okay. And then 32,400 minus 3,600 times 4. Oh my gosh, we nailed it. That was amazing. So the value is 18,000. That's the same value, okay? 18,000. So that was pretty creative. Even though the scale really wasn't great to work with, we still were able to get it right on, okay? Use the model from part A to algebraically determine when the nimbus is 0. So when we say the value, if I use this model, the model, by the way, is the equation, okay? When the value is 0, I would set it to 0, 25,200 minus 1,800x. So we would want to set the value to 0 and solve for x. How would I solve for x? Well, it was exactly the same thing we were doing before. We were just basically take 25,200, so we have negative 25,200 equals negative 1,800x. How do I get x by itself? Divide. Yeah. And that's how we got x equals, remember when we did that before, that's how we got the x-intercept. X equals 14, right? That's when the value is 0. Give the domain and range. Now this came from Math 60 as well, talking about domain and range. The domain is 0 to 14, and the range is, so the domain, do you guys remember what domain and range mean? Okay, domain are the x values. So remember how I said I wasn't going to put arrows on the end of my line? All linear equations usually have arrows on the end. Why did I say I wasn't going to include arrows? Yeah, you're not going to use negative time. So they're saying the domain, which are the x values, and in this case it's the years, I can buy it and I own it for 0 years, right? Right when I buy it, I own it for 0 years. And then after 14 years, the car is worth nothing. The value is 0. So at that point, it's maybe junk. I don't know. That's not really how it works in real life. But the range are the y values, and that's the value of the car. value of car. So what is the smallest value of the car that we can have? What is the largest value of the car we can have? This, yep, 0 to 2,500, or yeah, no, 25,000. You know what the number is, okay? So this is what we call our range. Now we put brackets on the end because those numbers are included, okay? When you put parentheses, the number is not included. When you put brackets, the number is included. Use the model in Part B to algebraically determine the limones when it's worth 0. It's the same exact thing, and it's the thing we already solved. This is when it's worth 0, was at 9 years. The way we did that is we said 0 is the value, so we're plugging in value of 0 equals 32,400 minus 3,600x. And we're essentially solving for x, right? So when you solve for x, you're doing the same thing here. Subtract 32,400, subtract 32,400. You guys knew this intuitively, how to find that number. You're like, well, I'm just going to divide how many years. If this is how much it's going down every year, I want to figure out, well, how many years until I eat away at this whole entire value. So we got x equals 9. And that was the same number we put right here, right? That's how we got that X-intercept. Because you see, on the x-axis, the value is worth 0. On the y-axis, that's our starting place. That means we've had the car for 0 years. Give the domain and range of the limones in the context of this application. The domain is what? Anybody have any ideas about what the domain would be? Think about the domain of the nimbus. So what's the smallest amount of years you can own it? And then when is it worth nothing? 0, 9. So we're going to put brackets around the 0 and brackets around the 9. That bracket means the number is included. Okay? 029, yes, because you can own the car for half a year. You can own the car for 7.5 years. You know what I mean? All the numbers from 0 to 9. This is what we call, actually, sorry, I should say this. This is called interval notation. Okay, in Math 60, we learned this in Chapter 2. So you can always go back and review domain, range, interval notation, function notation, functions, if you'd like to, okay? And that's going to be very helpful because we're going to keep, coming back to that. But it's also kind of like when in Rome. You hear it, you see it, and you're like, oh, okay, that's how it works. That's how math is sometimes, right? When in Rome. All right, let's look at the last page. And this is a very, very similar problem. 2 construction companies offer different pricing structures for jobs that they accept. Company A, $5,000 plus $15 per square foot of a building. Company B, $7,500 plus $12.5 per square foot of building. Construct a function. Actually, I think I'm going to let you guys, because this video is getting quite long, I'm going to let you guys, I think you can solve this based on what we just did. So I'm going to let you guys work on this one in groups, knowing that also the PowerPoint has the answer for you to look at as well. Okay?